All right, continuing on now. We need to look at an issue because every time you take a situation and say, okay, it is simple, you just do this, turns out when you really look at it, it's not always that simple. And we have another case right here, and this is when we have ionic compounds dissolved in water. Aqueous solution of ionic compounds, when we look at their colligative properties, things aren't just quite exactly what we want them to be. For example, when we looked at ionic compounds dissolved in water, if you recall when we were discussing osmosis, if we have 1 molar sodium chloride, we would expect that to have twice the freezing point depression as 1 molar sugar, because when sodium chloride dissolves in water, it dissolves into 2 particles, the sodium and the chloride. When sugar dissolves in water, it does not dissociate. It stays as a sugar, as a whole sugar molecule. So 1 molar sugar is 1 molar in particles. 1 molar sodium chloride is 2 molar in particles. Recall, 1 molar magnesium chloride is 3 molar in particles. So we would expect, if we looked at the freezing point depression for 1 molar sugar, we expect the freezing point depression of 1 molar sodium chloride to be twice that, because it has twice the number of particles. We'd expect the freezing point depression of magnesium chloride to be 3 times the freezing depression of sugar, but that is not the case. It's close, but not quite. We need to put in another factor into our equations when we are dealing with ionic compounds. So recall that our normal freezing point equation is the change in temperature freezing point, the freezing point depression that we measure, equals the freezing point constant times the molality. We need to add in this factor I, where I is the Vant-Hoff factor. And the deal is that these ionic compounds are kind of interacting with the water, interacting with the solvent, and so they don't give us the exact right results, but they do pretty close. So the Van Hoff factor, it's close to the number of particles per compound, but not quite. And it turns out the more concentrated the solution is, the smaller I is. So here's a little table, and let's see what this means here. Say we had a 0.0124 molar sodium chloride solution. Now normally, if we're looking at freezing point depression, we'd say, okay, the change in freezing point equals a constant times the molality, but note sodium chloride would be 2 molal in particles, so we'd expect whatever the molality of sodium chloride is, M would be twice that because it's 2 particles. We'd expect I, the Van Hoff factor, to be 2 if all things were good in the world, that the change in freezing point depression equals a constant times the molality of sodium chloride times 2 particles of sodium chloride. But it's not 2, it is 1.94. Now note, 1.94 is pretty darn close to 2. But it's not exactly 2. Instead of 2.00, it's 1.94. It's off a little bit. And that's for a 0.012 molal sodium chloride solution. If you bumped up the concentration quite a bit, a little over 10 times the concentration, to 0.137 molal, you'll see the Van Hoff factor drops from 1.94 to 1.84. Still, 1.84 is pretty close to 2. It's going away from it, but it's, 1.8 versus 2. It's not too bad, but it is less than you'd expect it to be. It's not 2, it's 1.8. Note, start bumping up the concentration more, 0.349 molar sodium chloride. Instead of 2, it is 1.83. All right. Note also, if, as we see here, the more concentrated the solution is, the smaller the Van Hoff factor is, the further it gets away from where it should be, and always smaller. The less concentrated the solution, the closer the Van Hoff factor is to where it should be, such that if you had an extremely, extremely dilute sodium chloride solution, 0.0000001 molar sodium chloride, we would expect that Vant Hoff factor to be essentially 2, like 1.99 or something like that. So that is something to watch out for. Question, where do you get these Vant Hoff factors? You gotta get them from a table. So that's the deal. Or, you can do math and compare what you expected to what you get and then calculate the Van Hoff factor. But for the most part, I will be coming from a table. And you should expect it, if you're doing it right, to be close to, I should be close to kind of what you're expecting. For example, if we're looking at the change in freezing point or boiling point and you have a magnesium chloride solution, you know the change in freezing point equals K for the freezing point depression for the solvent times the molality of the magnesium chloride times the Van Hoff factor, which you'd expect to be close to 3. You expect for magnesium chloride that should be close to 3. It's probably going to be something like 2.6 or 2.8 or something like that. All right, cool. So watch out for that. Note, if you're given a question on an exam where it's asking, okay, sodium chloride, how much boiling point elevation are you going to get by adding this amount of sodium chloride to a aqueous solution? And if you are not given the Van Hoff factor, if there's no way to get the Van Hoff factor, what they're saying is, at that point, do you realize that the molality of particles for sodium chloride is 2? So if you're not given the Van Hoff factor for an ionic compound dissolved in water, just assume it's what it should be. Sodium chloride, you'd expect it to be 2. Magnesium chloride, you'd expect it to be 3, because there's 3 times the particles. If you are, however, given access to Van Hoff factors, the actual number, then put those in there. All right. The last thing we're going to talk about in this chapter are colloids. And there's not a whole lot in my notes about colloids, but the book has some nice pictures. So let's look at some of the pictures in the book concerning colloids. And when you have a colloid or a colloidal dispersion, you have a situation where the particles that you're dealing with are actually kind of big. They're bigger than just sodium and chloride. They could be proteins or something like that, such that it's not a true solution, but it's also not a suspension. Recall, a suspension is when you have large particles kind of, well, for lack of a better word, suspended in that liquid, such that if you wait long enough, those large particles will fall to the bottom. My prime example of a suspension is good old delicious Missouri River water. Yeah, go to the Missouri River, get a cup of that water, and it's just brown, murky nastiness with pebbles in it and stuff like that. And if you wait a while, you'll note the brown and murkiness kind of settle to the bottom. That's a suspension. When you have a colloid, you have a situation where the particles are smaller than the particles in the suspension, so they do not settle out. You can leave it sitting for a while. The particles are not going to settle out. However, they're not truly in solution. Now, here's some examples of colloids here. You can have an aerosol, which would be a liquid and a gas. I'm not going to make you memorize this. What's an aerosol? What's a foam? What's in motion? Don't have to memorize this. Just know the general idea of colloids. So if you have liquid water drop, fog is an example of an aerosol colloid. You have liquid water droplets in the air, but they're not settling out to the ground. That would be rain. Fog is these liquid water droplets in the gas air, and they just make this colloid where it's tough to see the individual water droplets, but you know they are there. Note, and we'll come back to this, and this picture shows it, that when you have the street lights, note you can see the light moving through the fog. If you're driving through fog, you'll note that your headlights, you can see the path of the beams of your headlights through fog. All right, smoke is a solid aerosol, solid dissolved in, or colloidal suspension in the air. Foam, whipped cream, shaving cream is air bubbles in a liquid, gas in a liquid. That's a colloid. Milk is an emulsion. Two liquids, the fat globules, the milk fat globules and water is milk. Milk is a colloid. All right, and there are some liquids and solids like opal. And so that's the general idea of colloids here. And one thing how you can tell a colloid from not a colloid, just like the fog, is something called the Tyndall Effect. And what happens, the book has a nice picture of it right here. If I can get it on screen. All right. If you took salt water, just normal salt water, dissolved up, that's a solution, not a colloid. That would be like this over here. You can see if you shine a light through it, you cannot see the path of the light through salt water. However, if you have a colloid, you can actually see the path of light through the colloid. You can see the beam of light, the path of that beam of light as you shine through. So if you look at these two, it's like, well, that looks clear, colorless. That looks clear and colorless. How do you know if it's a solution or a colloid? Just like the fog, shine a light through it. Note this is air right here. You cannot see the beam of light going through the air. You can actually see the beam of light going through the colloid. And then when it gets to a solution, you can't see the beam anymore. Now, milk is a little bit chunky, but if you want to see the Tyndall effect on your own, make some Jell-O, and the lighter the color of the Jell-O, the better. But make some light-colored Jell-O, because Jell-O is a colloid. So make a block, a big old piece of light-colored Jell-O, and get a nice flashlight with a narrow beam and shine it through. And when you shine that flashlight through that Jell-O, you will be able to see the path of the light going through the Jell-O. Best probably to do it at night where you can turn the lights off and get it dark in here, but Jell-O shows the Tyndall effect because it's a colloid. All right, that is it for this chapter. We'll be moving on to the next chapter, kinetics, in future videos.